In this video we're going to look at indices, HCF and LCM. So the accepted shorthand of writing 2 times 2 times 2 times 2 is 2 to the power of 4. We can see that because there are 4 2's being multiplied together. The 4 is called the index or the power, and the 2 is called the base. When we're multiplying terms, we can't mix different base numbers. So in this first example, when we've got 2 times 3 times 2 times 5 times 3, we can see that there's the 2 times the 2, they're the same base, and we can express that as 2 to the power of 2. And then we've got 3 times 3, so we can express that as 3 to the power of 2. And there's only one 5, so it's going to be 5 or 5 to the power of 1. So we could write it as 5 to 1, but we generally don't. We just leave it as 5. We can't combine the 2 and the 3 or the 5 because they have different bases. Example B, then find the value of 3 squared times 5 squared. So 3 squared means 3 times 3 multiplied by 5 times 5. And then we have 3 times 3, which is 9. And 5 times 5 is 25. And 9 times 25 is 225. Product of prime factors. So there are a number of ways to do this. Now what this really means is we're trying to factorize a number. So we're trying to come up with all the numbers that divide evenly into another one. So we've already looked at if we were trying to factorize 24, we'd be thinking about 1 times 24, 2 times 12, 3 times 8, and 4 times 6. But whenever we're trying to write them as a product of their prime factors, we can see that 24, 12, 8, 6 and 4 aren't prime numbers, so we need to try and express them as primes being multiplied together. So what we do is we divide a number by all the prime numbers. So we start off with 2 and we keep going until we can't divide by 2 anymore. Then we move on to 3 and 5 and so on until the numbers are just to 1. And we can express the number as a product of the divisors. Or what we can do is we can write the number as a product of 2 convenient factors, and then repeat this until each factor is a prime number, and then we can express them as a product of prime. So we'll look and see how we do that in terms of these two numbers. So example 4, express 72 and 108. So what we can do is we can divide 72 by different prime numbers. So we'll start at 2, and 2 into 72 goes 36 times. We can divide 36 by 2 again to get 18, and we can divide by 2 again to get 9. 9 can't be divided by 2, so we move on to the next prime number, which is 3, and 9 divides by 3 3 times. We divide 3 again by 3 to get 1. And then the product of the divisors is the product of prime factors. So 72 is 2 times 2 times 2 times 3 times 3, which is 2 cubed times 3 squared. So we'll look at the different technique then for writing 108. So 108 we might think of as 9 times 12. But we know that 9 and 12 aren't prime numbers, so we need to try and express them as a product of primes. So 9 would be 3 times 3, and they're prime numbers, so they can't be reduced any further. 12, we could be thinking about 4 and 3, but again 4 isn't a product of primes, so we can express it as 2 times 2. So then if we combine these numbers, so the 3, the 3, the 2, the 2 and the 3, we get that 108 is 2 squared times 3 cubed, because there's 2 2's and there's 3 3's being multiplied together. So it's 2 squared times 3 cubed. So we can use this product of prime factors for working out square and cube numbers. When we write a number as a product of prime factors in index form, square numbers, each factor will have even powers. Cube numbers would have powers that are multiples of 3, and so on. So if we're looking at 5 to the power of 2, so the 5 has an even power, 7 to the power of 4 has an even power, and 11 to the power of 2 has an even power. And because the 2, 7, or the 2, 4 and 2 are all even, that means that 5 squared times 7 to the 4 times 11 squared is a square number. If we look at 5 cubed times 7 cubed times 11 to the power of 6, the power of 5, the power of 7, and the power of 11 are all multiples of 3. That means that this number, whatever it happens to be, is a cube number. And if we look at 5 to the power of 6 times 2 to the power of 12 times 17 to the power of 18, we can see that the powers are all even. So that means it's going to be a square number. But also the powers are divisible by 3. So that means it must also be a cube number. So example A, write 4,410 as a product of prime factors. What is the smallest number you can multiply it by so that it's a square number? So let's use the ladder method for 4,410. And we can divide it by 2 to get 2205. So it's no longer divisible by 2, so we need to check the next prime number. And if we add the digits, 2 plus 2 plus 5 is 9, so that means it's divisible by 3. If we divide by 3, so 2 into 20 goes 7 times, remainder 1. 3 into 10 goes 3 times, remainder 1. And 3 into 15 goes 5 times. Again, the digit sum, 7 plus 3 plus 5 is 15, so that means it's divisible by 3. So we can divide by 3 again, so 3 into 7 goes twice, remainder 1. 3 into 13 goes 4 times, remainder once. And 3 into 15 goes 5 times. Doing the digit sum this time gives 11, so it's no longer divisible by 3, so we can go to 5. So dividing 245 by 5, so 5 into 24 goes 4 times, remainder 4. 5 into 45 goes 9. That's not divisible by 5, but we should know that that's divisible by 7. And 7 into 49 goes 7 times. Again, we can divide by 7 to get 1. So we always try and get down to 1. So 4,410 is 2 times 3 squared times 5 times 7 squared. And what we can see is that the 3 has an even power, as does the 7. So what we want for a square number is that all the powers must be even. So what we need to multiply, if we multiply this by 2, we'll get 2 squared. And if we multiply by 5, we'll get 5 squared. And that would mean all the powers are now even. So multiplying by 2 and then by 5 is the same thing as multiplying by 10. So that's the smallest number that we can multiply it by to make it a square number. Obviously we could multiply it by itself. So we could have done 4,410 multiplied by 4,410, and that number is definitely a square number, but the smallest number would be 10. Example B, 91,125 converted into 3 to the power of 6 times 5 to the power of 3. Find the cube root of that number. So what we need to do to find the cube root is we divide each power by 3. So the cube root of that number is going to be 3 squared times 5, or 5 to the power of 1. Now the justification for that, by dividing each power by 3, is if we're trying to cube a number, we multiply it by itself 3 times. So we'd have 3 squared times 5, multiplied by 3 squared times 5, multiplied by 3 squared times 5. So here we've got, looking at the 3's, you'd have 3 times 3, times 3 times 3, times 3 times 3, which is 3 to the power of 6. And looking at the 5's, we have 5 times 5 times 5, which is 5 cubed. So here what we've done is we've multiplied it by itself 3 times, and we've found that it goes into the original 3 to the 6 times 5 cubed. Therefore, our process of dividing each power by 3 was correct. So to find the cube root, we divide the powers by 3. If we're trying to find the square root, we divide the powers by 2. And so on. And then our last example, by considering the product of prime factors, find the square root of 30,625. So what we need to do is factorize that. So we can't divide that by 2 because it doesn't end in an even number. If we do the digit sum, 3 plus 0 plus 6 plus 2 plus 5 is 16, which is not divisible by 3, so then we have to go to 5. So 5 into 30 goes 6 times, 5 into 6 goes once, remainder 1. 5 into 12 goes twice, remainder 2, and 5 into 25 goes 5. Again, we can divide by 5. 5 into 6 goes once, remainder 1. 5 into 11 goes twice, remainder 1. 5 into 12 goes twice, remainder 2. And 5 into 25 goes 5. Again, this is divisible by 5. 5 into 12 goes twice, remainder 2. 5 into 22 goes 4, remainder 2. And 5 into 25 goes 5 times. Again, we can divide by 5 again. 5 into 24 goes 4 times, remainder 4. 5 into 45 goes 9 times. 49 is divisible by 7 to give 7. And we need to end up at 1, so we need to divide by 7 again. So what we have is that 30,625 is 5 to the power 4 times 7 squared. And if we want to find the square root of that, we divide each power by 2. And we'll get 5 to the power of 2 multiplied by 7 to the power of 1, or 5 squared times 7. The HCF and the LCM. So the highest common factor is the largest number to divide evenly into whatever the given numbers happen to be. The lowest common multiple, or the LCM, is the smallest multiple of each of the given numbers. So the LCM is the number that's bigger than the two numbers, or the three numbers, or however many it has to be, whereas the HCF is a number that's smaller than the given numbers. So our method of doing this is expressing it as a product of prime factors, and then we look for the common factors, and those will be the HCF. And then if you multiply the HCF by all the other numbers, that will give us the LCM. Now there is a method to use Venn diagrams, and we'll show both of these in this example. So factorising 112 gives us 2 to the power of 4 times 7. So we've done quite a few examples on that, so hopefully we're happy enough where that comes from. And 264 is 2 cubed times 3 times 11. So one way we can do this, so if we list the factors, 2 times 2 times 2 times 7, and 2 times 2 times 2 times 3 times 11, and if we look at the common factors, so we can see that there's 2 common, and another 2, and another 2, but there's nothing else in common between the two numbers. So that means that the HCF is 2 times 2 times 2, so we count each circle as once, and we get the HCF as 8. The LCM is going to be the HCF multiplied by the other numbers. So that's 8 multiplied by 2, multiplied by 3, multiplied by 7, multiplied by 11, which gives us 3,696. Or I said we could use this with a Venn diagram, so I'm going to do that. So if we look at the numbers of 100, or the factors of 112 and 264, well, we can see that there were three 2's common, and then there's a 2 and a 7 within the 112. Within the 264, we still need the 3 and the 11. So what we have is that the HCF is the overlap, so that's going to be 2 times 2 times 2, which is 8, and the LCM is going to be 2 times 7 times 8, the HCF, multiplied by 3 times 11, which gives us our 3,696, as we had before. Example 7, 120 Year 8 students and 96 Year 9 students are to be split into groups. With the same number in each group, what is the largest possible size? So we're looking for largest here, and the largest is going to be the HCF. So we're going to look for the HCF between 120 and 96. 120, we can factorise that and write it as a product of primes to give 2 times 2 times 2 times 3 times 5. And we do the same with 96 to give 2 times 2 times 2 times 2 times 2 times 3. So if we look to do a Venn diagram, 120 and 96. So we can see we have 1, 2, 3 2's common, but we also have a 3 common to both as well. So we'll put a 3 in there. Then in the 120 circle we're missing a 5, and the 96 we're missing 2 2's. And because we're looking for the HCF is going to be 2 times 2 times 2 times 3, which is 24. So the largest group size is 24.